Hello everyone, I'm very happy to share our work Hermes Attack. This work aims to steal the DNA models in AI privatization deployment scenarios. Before we go to details, let me introduce the speakers and collaborators. I'm Yueqiang Cheng. I'm from Baidu Security Research. I'm working on the system security like SGX and SUV. And also some hardware securities like Hermes and microarchitecture vulnerabilities like spectrum and stuff. Mr. Yuankun Zhou working on the GPU security. This work is mainly done during his internship at Baidu. Dr. Husheng Zhou working on the GPU, HPC, and some security stuff. Is working in the VMware. This work we're using the Hermes as the work name because Hermes is the master of shifts and the god of steals. And this work we also published at Unix Security 2021. The full version is accessible on the archive. Now let's talk about some motivations. The AI services is used everywhere, from the autonomous driving to the privatization deployment. Lots of big tech and big vendors in these areas. So typically people need a very big data and tens of the GPUs to training and get very high quality DNA models. It's not cheap. Typically you need like $1 million of 400K to get very high quality services to deploy the commercial services. So face such situations, the attackers may propose, say, okay, can we steal some information? And there's some existing work indicate that the attackers can leak the architectures, the hyperparameters, and the parameters. However, all of them can only reconstruct the partial model, meaning none of them can fully reconstruct the whole DNA model. And the Hermes Attack is the first work that can fully steal the DNA models with zero inference accuracy deductions. The virtual scenario, the left side is the host. There's some AI services executing there, and the operating system, Windows, Mac OS, and Linux, and the hardware layer connected to a GPU through the PCIe bus. And we identify there's some PCIe bus could be a new attack surface and is highly risks in this AI privatization environment because attackers can physically access this working environment and they possibly to install some sniffing devices on the PCIe bus to steal the data. This is some background, the DNA stack, system stack. The up layer is AI services and the framework layer, the TensorFlow, PyTorch, PyTorch, and the CUDA OpenGL run upon the GPU runtime. And the GPU driver in the kernel space communicate with system calls like IO control. And the bottom layer is the GPUs. They connected to the system through the PCIe bus. And the working mode, like the CPU and GPU, they connected through the PCIe bus. So the GPU is a passive device. So each time they want to run some services, the GPU will issue a command. So here the host will send to the data, send to the code, and launch the kernel. After the finish, the kernel will generate some output and send back to the CPU side. So this working mode, we have two observations. One is totally the command-driven interaction mode, and the second observation is all data and code are passed through the PCIe bus. So this inspired us. So it's highly possible we get the information by intercepting the PCIe bus. However, the attack is not that straightforward. There are many challenges there. The first challenge is coming from the closed-source code and undocumented data structures. So all these obstacles ask us we have to do the reverse engineer, the loss of the effort and the manpower in this topic. And the second one is the numerous noises and the out of orders in PCIe packets. So we have to do the sanitization to filter out all the parameters, and we have to carefully. We cannot filter out the useful package. We only can filter out the noises. And we have to do the order correction to correct the order, make them in the correct order. And the third one is the semantic loss in the PCIe traffic. On the host side, the GPU driver maintain everything. They know the semantic, but it does not necessary to send out this semantic information to the GPU side. So only issue the command. You just do this. However, in this situation, we cannot intercept the semantic information. So the loss of the semantic information, we have to using some other information to reconstruct the semantic. So let me go over the attack overview to say how to overcome the above challenges in our work. So this is the attack overview. From the original model, we have to install a device to do a PCIe intercepting, and then we go to the traffic analysis. We remove the noise, we get in order traffic, and then we extraction the useful information like the command, because it's a command driven working mode, and then we do the reconstruction to reconstruct the architecture, hyperparameters and parameters, and finally we get the generated model. We expected the generated one is the same as the original one in terms of the inference accuracy. So let's first talk about the PCIe interceptors. Now this is our test working bed. So we are using this GPU. The GPU we working three kind of GPUs: the NVIDIA Enforce GT730 and the RTX 1080 Ti. RTX 2080 Ti, and the interceptor we're using the PCIe protocol analyzer. And the DNN models we're working on the MNIST, VGG, and the ResNet. Just some terminologies. We can say there are some PCIe packets. The PCIe packet can divide into two parts. One is the header, other is PCIe payload. The header, there is lots of field to indicate some different meaning, and the important one is the tag. And the payload will contain the command. The command also divided into two parts: is command header and command data. Command data will have the weights, the command and the kernels. So all useful information will in this part. So the tag is very important to indicate the package relationships. If the tag value is the same, we can link them together to say there is some upstream package and downstream package, and the address and payload can link also through the tag. Okay, let's talk about the traffic processing stage. There's some quick facts. The loss of numerous noises there. This only using the MNIST as an example. So we intercept over 1 million packets, but the useful package is quite a small portion, like only 20,000 packages. That's meaning up to 98.3 packages are noise. So we have to carefully pick out this small portion of the useful packages and remove all the others unused part. And we also found out there are some out of order issues. You see this two part is out of order. So this out of order issues is everywhere. We have to address them. So let's talk about the high level idea how to solve this problem. Like P3 is generated packet from the PCIe protocol analyzer. They have the downstream package ID and the upstream package ID and the content. So we observe that the upstream packages are in order. So we're starting from the upstream packet. We through the tag, this is the tag, to link to the downstream packet. And the downstream packet and also through the package ID will go to a row of in this package array. And this will be also corresponding to the upstream ID to double confirm we get the correct link. This is a loop. So and then we will sort the upstream package ID and generate the final package. This is the P3 prime. And we found out this order is in order. So but this part is off order. Okay, let's go to the second part. The second part is extracted the header and the command. Okay, let's talk about the GPU command. The GPU, the driver will put the GPU command into a ring buffer, and the GPU will fetch the command from this buffer. It's like a model of the pub and sub. So each GPU command have two parts. First is the side, second is offside. So offside there is command buffers. So the offside is from the base to some location. This is the offside. So starting here, and how large of data we should transfer using this CPU command. So this is the working mode of how GPU command works here. And there are lots of the GPU types, like the GPU initialization command, synchronization command, data movement command, kernel launch commands. So for our work, we only interested in two kinds of command. First, the data movement command, we say is a D command, and the kernel launch command, we call it a K command. So we identify this D command and K command through offline training. Later, we'll talk about how to do this offline training to build these command relationships. So the extract header from PCIe packet. There are lots of we need to do the reverse engineer. There are some field like address field, size field, and the type field. This is the important part. We should using this type to understand the command type. However, even we know the command, it's not easy to get the command extraction finished because there's some corner cases there. Let's take an example. Here the split command headers. As we highlighted, this is the whole command, but it's separated into two PCIe packets. So we should realize these issues. The second is the command data noise. So the command here, so the following should be the command data. However, there may be some noise between the command and the data. So we also should handle this part. So all this, we should check the address consistency. So we find out the address is not consistent. The first one and the second one. The third one, the first one should go to the third one. This should be connected, consistent. However, is in the real case is much complex than what we the examples here. So we also introduce the max distance scan distance. So if you want to know the details, you have to go to our paper to read all the details. Okay, the third one is the semantic reconstruction and model reconstruction part. The semantic reconstruction is challenges because the layer type information is lost in the PCIe traffic. As I mentioned, the CPU side, the driver has this information, but during the traffic, there is no such information at all. And we also observed each layer is completed through several kernels, and each kernel is launched using a K command. And the K command have a address point to the kernel binaries. So we also identified, so each kernel have a unique kernel binaries or some unique kernel binary combinations. So this inspired us, why not we build a database with the pair of the kernel binaries and the layer types. So if we have such information, we can reconstruct it for unknown black box DNN models. Okay, so how to do this offline database generation? We have some existing known DNN models, and each time we only using a single layer. Using this single layer, we trace, we do the inference, and we collected the kernel trees layer types, and we put them together. Because we exactly know the single layer, the type, and we collected the kernel binaries, so we know the relationship between them. So finally, we put all this information into a database. And this will service for some unknown DNN models. Is black box DNN models is the same thing. We can using this to query the kernel binaries or kernel binary combinations to identify the layer types. So we go to the model reconstruction. Model reconstruction have three sub-steps. First is the architecture, reconstruct architecture, reconstruct the hyperparameters, and reconstruct the parameters. So let's talk about the first step. So the architecture is straightforward for the sequential DNN models like MINIST and VGG, because they are the order is there, so we just record them and remove the noisy, but doesn't affect the orders. However, this doesn't hold for the non-sequential DNN models like the ResNet. To address this challenge, we introduced the data flow graph solutions. So for each layer, we record the output and the input. If the input is some layer's output, so there is a link, there's an arrow here to indicate the data dependencies. So repeat this step, we build this graph. And this graph will reconstruct the DNN models, the architecture. Okay, let's talk about the second step, the reconstruct the hyperparameters. To reconstruct the hyperparameters, there are two sources. One is we can directly obtain from the PCIe the packet. So like the kernel size, stride, filters, they're already there. We just know the offset and the location. We directly read the data information. Like the kernel size, this is the 3 times 3. And some we have to do the infer. Like this information doesn't contain in the PCIe package, but we can infer from the following operations, like the activation function and the use bears field. Like if we check the use bears, and the following how the bears activate the layer, so if we observe this the bears layer executed there, so we know the use bears should be checked. So based on this relationship, we can infer to reconstruct such kind of the hyperparameters. And the third step is to reconstruct the parameters. The parameter typically we call it width. The width is not that easy because width is mixed with the noises. And at the beginning, we have one assumption to say the weights maybe should be in the range of the -1 to 1. However, later we found out it's not always true for all the DNA models. So we gave up these assumptions. And we also found out there is no direct connections between the kernel launch command and the weight address. Previously, this observation is hold for the kernel binaries, but it doesn't hold. This relationship, these connections, doesn't hold for the kernel launch command with the weight address. Later, we zoom into this issue. We found out why this happened. We found out the cooldown memory copy device to device. There is device to device memory copy happen in the GPU side. So the GPU copy the weights from one location to another way. Of course, it's also driven by some command. So we have to following this copy event and just the arrows, and then we know the final destination of the weights. So following these arrows, we can get the starting address of the weights. So the next question is how we know how many number of weights there. We have to reconstruct them. Okay, for number of weights, there are some formulas we summarized. The weights one is like here the examples. Number of weights is the kernel weights, kernel height, and the input filter maps and output filter maps. The times together. And for different layers, the formula will change a little bit. So we summarize all these formulas. We can know, okay, we know the type, we know how to calculate. So we have the starting address, we can get the whole width there. Okay, let's talk about some evaluations. So we do the evaluation using three models, the MINIST, VGG 16, and ResNet 20. And we also have recorded the number of layers, number of parameters, data size, and the input shapes. Let's talk about the MINIST architecture comparison first. So this will visualize the layers. So for this, we can find out the first is original model and this the generated model. There are two differences. One is the dropout. Dropout layer is only used in the training stage, doesn't used in the inference stage. So in our attack, we run the inference. We doesn't capture this dropout. Actually, it doesn't used in the inference stage, so it doesn't affect the accuracy. The second is here. There's a convolution layer with ReLU. So the ReLU was separated. We treated the ReLU layer as a separated layer. So this doesn't change the semantic meaning. It's just to make it easily. For the VGG architecture, also the first is original, second is generated. We also find out all the dropout layers that we remove them, and we also find out some the density layer and the ReLU layers there. Here we also compare with the ResNet, the original one and the generated one. All of them the same until the last one. Again, for the activation function like the softmax and ReLU, we treat them as a new layer, so they are semantically equally. So we keep them as a separate layer. Okay, we also do the accuracy and efficiency evaluations. So we're using the also the MINIST VGG ResNet for the accuracy. So we can find this original accuracies and on different platforms, the JT730, 1080 Ti, 2080 Ti. So all of them we say is the same accuracy, always the same. So this indicates we fully instructed the model. There is zero accuracy reduction. And we also do the inference timing efficiency, that is in second. We can also find they are almost the same thing. There's no big difference. Finally, we also do the evaluation on the reconstruction performance. So we reconstruct the number of command, number of K command, number of completion packet, and the generation timing. So we can say the reconstruction performance is quite efficient. Typically, it's from 5 minutes to 17 minutes. So average is 10 minutes. We can do the reconstruction step. Okay, let's show some demos to show how we do this Hermes attack. So the intercepted PCIe protocols on 3 NVIDIA GPUs. So this original model and get the accuracy, and we do the reconstruction step. And this on the GT 730. And we found out the accuracy is the same on the GT70. And then we changed the device to the 1080 Ti. And we first do the reconstructing because we on different device we capture different PCIe packages. We should do reconstruct the model again. And we also fully reconstructed and we test the inference accuracy. Also the same accuracy. Finally, we set the device to the 2080. We do the intercepting and reconstructing again, and to reconstruct the whole AI model on the new devices. So okay, finished. Let's go to say test the accuracy. Okay, also the same. Okay, let's talk about some countermeasures. First, we have some hardware countermeasures, like we using the GPU encryptions and the PCIe encryptions. However, all such solutions need the hardware modification. Like GPU side, you have to significantly change as the encryption model. You build an end-to-end communication channel with the CPU, and there are lots of challenges there. How to share the key, how to manage the keys, and again for the PCIe encryption, you have to change the PCIe protocols, also change the PCIe controller, and all the devices attached to the PCIe bus. This cannot finish within a short period of time. So this solution may be help in the future new architecture system, but for the commodity operating system, doesn't help. For the software solutions, one is to do the obfuscation. Like this idea from the binary obfuscations, they will significantly increase the bar for the attacker to the reverse engineer. But obfuscation essentially doesn't completely solve this problem. The only effect is increasing the bar. The second one is offload partial task onto CPUs. That's this idea is say we split the task. One is on the CPU side, all others on the GPU side. However, this solution doesn't fully utilize the power of the GPU. Why we offload the AI services to the GPU? Because the GPU is more powerful than the CPU run such kind of operations. So such solutions will significantly reduce the efficiency of the AI services. So all these countermeasures doesn't perfect. They indicate our work needs lots of effort to investigate to mitigate these issues. So some takeaway: the Hermes attack is the first attack that can fully steal DNA models. all previous attacks only can partially reconstruct the models. We also support multi-platforms, multi-GPUs. So all these technicals doesn't the platform independent. It is platform independent. It's very hard to defend either from hardware way or the software way. And all the GPUs are not safe under our attack. So we also hope many people join this area to enhance the GPU security. There's some reference we are using in our work. Okay, thanks. Any questions are welcome. Thank you.